So this is the final lesson in Unit 910. This is material out of Box G here, and we're taking a look at higher derivatives here. And when we're talking about higher derivatives, basically what we're doing is we're taking the derivative of a function that we have already taken the derivative of. So we can start by talking about the second derivative. The second derivative of a function is the derivative of the original function. So if I have some function f at x, I take the derivative, I get f primed at x. We could call this the first derivative, okay, because I've taken the derivative once. If I go ahead and take the derivative again, I get the second derivative, which we denote by f double primed at x. So second derivative, we just add another primed into our notation there. Or we could have something like y to y primed. Second derivative would be y double primed. Or if we had, let's do y again. The other notation was, for our first derivative, was dy dx. Second derivative would be d squared y over dx squared. Okay? So that's just the notation. Okay? So let's do a quick example here. I've got a function y equals 6x to the power 4 minus 3x squared plus 7x minus 2. And if I take the derivative, y primed, I get, well, I can do this term by term, apply the power law here to get 4 times 6 is 24, x cubed minus 6x plus 7, and that negative 2, because it's a constant, is just going to go away when we take the derivative. Derivative will be 0. Then I can go ahead and take the second derivative here. So that's just taking the derivative of y prime there. So my exponent is 3. I do 3 times 24. That's going to get me 72. 3 minus 1, so I get squared for my exponent. My next term here, I got an exponent of 1. That'll give me negative 6. Take 1 away from the exponent, I get 0, so the x's are gone, and the 7 is my constant, so it goes away when I take the derivative. So there's my second derivative. Okay. So same sort of thing with this slightly more complicated example here. If I'm going to take the derivative of this thing, first I want to write it in a form where I know what those exponents are. So this is going to be 2x to the power of 5 over 3, because I'm taking the cube root and I'm putting this to the 5th power, minus 4 times x to the, well, I'm taking the square root and I'm cubing it, so 3 over 2. And again, I can just apply my rules of differentiation. F primed at x is going to be 5/3. I should do it the other order here. Keep the 2 out front because that's my constant. So 2 times 5/3 x to the 2/3, subtracting 1 from 5/3, minus 4 times, I'll get 3 over 2, times x to the 1/2. And then I can clean this up a little bit. 10 over 3 x to the 2/3 minus 6 x to the 1/2. My second derivative, I just repeat the process. So bring down my 2/3, so I'll have, I'll put the 10/3 out front. 10/3 times 2/3 x to the negative 1/3 as I subtract 1, minus 6 times 1/2 x to the negative 1/2, and clean this up again. So we'll get 20 over 9, x to the negative 1/3 minus 3, x to the negative 1/2. Did I do that right? Yeah, it looks good. And I can just put this back into radical form here. So I'll have 20 over 9 cube root of x minus 3 over root x. And I'm done. Okay? So again, we're just taking the derivative of our derivative. Now, the biggest application is going to be in these kinds of position velocity questions that we did in the last lesson. So let's take a look at a sort of sample question here. The position of an object is given by the function. S is a function of t, is this big long thing here, where we're restricting ourselves to the interval t is between 0 and 10. We want to find the velocity and the acceleration at t equals 4. Well, we know that our velocity is the rate of change of position equals rate of change, rate of change of position. So this is just, our velocity function is going to be the derivative of our position function. That's what we did last time. Well, what about acceleration? How is acceleration related to velocity? Well, velocity is the rate of change of position. Acceleration is the rate of change of velocity. Rate of change of velocity with respect to time. So if we want an acceleration function, we're going to take the derivative of our velocity function. Or a at t is v primed at t. But v primed at t, well, our velocity function is already the derivative of our position function, so acceleration is just the second derivative of our position function. Okay. So to answer this question here, we need to find our velocity function and our position and our acceleration function. So let's see. Our velocity function, we're just going to take the derivative of our position function. So that's going to be 3t squared minus 12. And if we want the velocity at time 4, we just sub in 4 here, and we get 36. To get our acceleration, we're going to take the derivative of that velocity function that we just found, v primed at t. So we differentiate 3t squared minus 12. Let's see, we bring down the 2, we get 6t. The 12 goes away, and we just have 6t. So our acceleration at t equals 4 is just going to be 6 times 4, or 24. So the last thing I want to do here is just take a look at how you can interpret position, velocity, and acceleration graphically. Okay? So what you have here is a graph that shows the position function of an object. So this is the position as a function of time with respect to time here. Okay? And the first 3 questions here are asking us not about the position, but about the velocity. When is the velocity 0? When is the velocity positive? When is the velocity negative? So if we're talking about velocity, but we have a position function, we have to remember that velocity is represented by the slope of the tangent to the position function. So if we're talking about velocity, we are looking at the slope, I should say velocity, is slope of the tangent to this function that we have here. So to sort of answer these questions, we should take a few points here and visualize what the slope of the tangent is going to look like at each of these points. So if I come to like a point right here, and I draw the slope of, and I want to draw the tangent to this curve, I'm going to draw something like this. If I come over here and I draw it, the tangent is going to look kind of like this. I come down here, tangent will look like this. And if I come over here between D and E and I draw my tangent, it's going to look something like this. Now, the two key points that I've skipped over here are B and D. What's the tangent going to look like at point B and at point D here, Austin? It's going to be horizontal, yeah. Okay. So this basically gives us the answer to question number A here. At what points on the graph is the velocity 0? Well, if we want the velocity 0, that tells us that the slope of the tangent is going to be 0, which means our slope is, our tangent is horizontal. Well, let's just try all this again here. So let's just say tangent is horizontal, i.e. slope equals 0. So we're looking at points B and D. Okay. Question B asks us, during which intervals, okay, this is interval from one point to the next, is the velocity positive? So we have to look at each of these tangents that we've drawn and say, which of these tangents, or in what sections of the graph, is the slope of the tangent positive? Well, positive slope means this is going up as we go from left to right. So this one right here that we've drawn at the beginning certainly has a positive slope. And anywhere between points A and B, it's going to have a positive slope. So A to B. Where else is it going to have a positive slope? Yeah, between D and E. Now, question C is asking us sort of the opposite. Where's the velocity going to be negative? Or where's the slope of the tangent to the curve going to be negative? Well, that's pretty much everywhere that we haven't already talked about. So that's going to be from B to C and from C to D. Okay. The next two questions ask us about not velocity, but acceleration. During which intervals is the acceleration positive? During which intervals is the acceleration going to be negative? So if we're thinking about acceleration, we're not thinking about the slope of the tangent anymore. We're thinking about how the slope of the tangent is changing as we go from one point to the next. Okay, so I'll just draw a line off here and say, how is the slope of the tangent changing? Okay. If the acceleration is positive, the velocity is increasing. So if the velocity is increasing, the slope of the tangent must be getting progressively steeper. So where is our tangents getting steeper? Okay? Or sort of, I shouldn't say steeper, the size of the velocity getting larger. What do we think here?
I think it's linear, like, so it'll start off in a negative direction, or, yeah.
Yeah, that's what the graph will look like. Okay, so it's going to start off negative, and it's going to end up positive. So basically, if we're looking at intervals here on this graph here, we can start, if we start at A, okay, our slope is kind of like this. And as we move along, we get to B, it's got to get down to 0. So it's got to be decreasing as we go from A to B. So from A to B, if the slope of the tangent is decreasing, okay, our velocity is decreasing, so our acceleration is negative. So our acceleration is negative from A to B. If we go from B to C, we start off as 0, and now our slope is becoming negative, and it's getting more and more negative as we move from B to C. So the slope is still decreasing. It started as 0, it's getting more negative. So our velocity is still decreasing, so our acceleration is still negative as we go from B to C. Once we get to C, though, okay, if we imagine going from C to D, by the time we get to D, we have to be back up to 0 again. So between C and D, our slope of our tangent has to increase back up to 0, so our acceleration has to be positive. So C to D. And from D to E, it's going to keep on increasing, okay, because it's getting steeper and steeper, okay, with a positive slope as we go from D to E. Okay. So our acceleration is negative from A to B and then B to C, and then it starts being positive from C to D and then on to D to E. So we can use all of this information on the back of the page here to sketch the corresponding velocity and acceleration graphs. So flip the page over there, and you got two axes, blank axes here. You've got, this is our original position function. This is going to be our velocity function. And this is going to be our acceleration function down here. So if we're given a position function, the first thing to take a look at is the points where the slope of the tangent is 0. So we identified point B and point D as having horizontal tangents here. So these 2 points here, B and D, correspond to points where our velocity is going to be 0. So if we go down to our velocity graph, let's just put a little dotted line here, okay? So if we go a little bit past 1 here on our velocity graph, our velocity has to be 0 right there. That's point B. And same thing over here, just a little bit before 5 is going to be another point where this is point D, where our velocity has to be 0. Okay? Halfway in between these two is going to be point C. So point C is sort of right here in the middle. Let's put it right like this. Okay. Now we said that from A to B, the slope of our tangent was getting smaller. It starts off positive, okay, but it gets smaller and smaller and smaller until by the time it gets to B, it's down to 0. So our velocity has to start off at positive values, get smaller, and then when it gets to point B, it's right at 0. Then from B to C, the slope keeps getting smaller, okay? But then from point C to point D, it turns around, and it has to get back to 0 for point D. And then from D to E, the slope just keeps on increasing. So this thing is going to go kind of like this. We'll put E way over here at something like this. Okay? So this would be the graph of our velocity. Now notice that if we look at our position function here, this is a cubic function, right? Something that is of the order t cubed. Our velocity function is a quadratic. It's a parabola, so something of the order t squared. Because as we've taken the derivative, going from our position to our velocity, we subtract 1 from the exponent. Which suggests that when we get down to our acceleration, instead of it being quadratic, it's now going to be linear, something of the order t. Now, if we're going from our velocity to our acceleration graph, we're looking at the slope of the tangent to the velocity graph. So let's look for the place where our velocity, or the slope of the tangent to the velocity, is 0. Okay, so if the slope of the tangent is 0 there at C, that point right here has to be where our acceleration is 0 at C. Our velocity is, well, let's see, let's look at the slope here. If our slope is negative, 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 it hits 0, then it becomes positive, positive, and positive. So our acceleration is going to go from a negative value to 0, and then to a positive value. And it's going to be a linear function. So it's just going to go just like that. And there we are. Position, velocity, and acceleration graphs.